Yeah, so it's going to be kind of, the topic is sort of similar to the last presentation, but I wanted to kind of present something that we've been working on for quite some time. So it's called Biscotti. We love Italian cookies, apparently. So this is basically trustless light client infrastructure for blockchain. So what we're looking at is essentially some of the stuff that everybody in this room has been talking about for a while. How do we build efficient ZK light clients for different blockchains? I should mention also, this is joint work with a bunch of folks at Jump Crypto over here. So, all right. So we started with Ethereum, obviously, because I think most people in this room understand why. So I'll just give kind of a brief overview of what the consensus protocol for ETH looks like and what we're trying to actually prove. So the Altair hard fork introduced this light client specification, which allows cheap verification of the chain's consensus with minimal bookkeeping. What that means is basically you have this sync committee that has a set of 512 validators that are uniformly subsampled from the entire set of validators, which is around 400,000. All right. So here are the few components I think that that are in this proof of consensus. So we have the BLS SIG verification. We have the simple serialize and RLP. So simple serialize and RLP are the serialization libraries that ETH uses. SSZ is for the ETH2 consensus protocol, and RLP is for the ETH1. There's a few components underneath, the Merkle inclusion proofs that you need to do, and the SHA function implementations that you need to do all in circuit. So take a quick look at this, but I'll kind of dive into each one of these components, and then we can kind of feel free to ask questions on these as well. Okay, so what does the architecture actually look like? So let's take a really simple example. We have a trusted block, we have an attested block, and we have a finalized block. Okay, so I wrote these in the order in which you might think about proving them, not necessarily the order in which they actually happen when you're actually running this protocol. So let's look down at the component diagram below. So the trusted in the trusted stage, you're basically doing a bunch of Merkle inclusion proofs. You have to do these Merkle inclusion proofs also in the finalized stage, but effectively we're doing something that was similar to what the ZK tree folks talked about, where you're basically doing these inclusion proofs within your circuit. And then we also have the BLS signature verification. So I won't delve into kind of the details of exactly what you need to prove in this, because it does get a bit hairy, but this is kind of the sort of keep this basic architecture in your head. All right, so what does the implementation look like? Obviously, I think a bunch of folks in this room also understand kind of what the various proof systems look like in the world. This was kind of our criteria for choosing a proof system. We want this to work really fast and really well in production. So we obviously need fast recursion. We don't want a trusted or necessarily universal setup. We want super fast proof generation. We want the developer ergonomics to be really nice. And the other thing that we're looking at is kind of community support and interest, right? We want to go with the things that people are kind of converging on in the industry, like where's the puck going, and we want to be there. All right, so this is kind of the breakdown of the primitives that we have built in circuit in BlockE2. So we have SSZ, RLP, two hash functions, SHA-256 and Ketchak, and then obviously the BLS signature implementations, which I'll also dive into, which contain a lot of different components, including the base and scalar fields, the extension fields, doing hash to curve, doing the pairing, all in circuit. So let's talk about the non-native operations for a second. So as many of you know, BlockE2 is written over the Goldilocks field. So this is a 64-bit field. It's great for super efficient recursion. It's also great for efficient proof generation, but it doesn't really support these non-native field operations that you really need for some of the work that we're doing, especially with BLS signature verification. So the ECC operations like point addition, whether it be affine or projective, you have these point multiplication, affine or projective, and then you have these extension towers that you also need to build in. So we have to build in the quadratic extension, the quartic extension, the sextic extension, and the 12th degree extension, all for doing the pairing, the Miller loop, and the final exponentiation for the BLS signature verification. So all of these components didn't exist in BlockE2, and now they're available. The code will be up soon, but these are kind of the different components that we had to build in. All right, so let's talk about the hash functions for a second. So there's two main hash functions that we need to use, SHA-256 in in the RLP case, and then the Ketchak hash function implementations in circuit. I won't delve into the details of like exactly what we did with the hash function because we're going to be talking about this in more depth in future posts that we'll make. But effectively, we have an optimized hash function implementation using like interleaved bit representations that make doing these computations in circuit much faster. So the high-level overview is that if you represent a set of bits as like this interleaved representation, you effectively interleave them with zeros. You can do an AND and an XOR operation in a single sort of addition instead of relying just on doing these separately. So, all right. Okay, now let's go into the BLS signature verification. So, as many of you know, also the ETH2 beacon block signatures are constructed over BLS 1231. And the BLS signature verification algorithm uses a pairing. And there's a bunch of different components within the pairing. So first, with the Miller loop, that contains doing things like line add or line double, and then evaluating those. But all these operations are kind of in your 12th degree extension. The final exponentiation also requires just sort of like simple exponentiation, doing like Frobenius, doing like these operations over the 12th degree extension as well. And then we also want to check that the signatures are actually within the right group. So we have to do an efficient like sort of subgroup check using, there's a few papers out there that we've looked at as well. And so this requires you doing like an endomorphism. There's another component with hash to curve, which requires a bunch of different components as well. And so I just kind of wanted to give a sense of like what the complexity looks like when you're trying to implement BLS like within BlockE2 or within some of these proof systems. All right, so this is the last component that I'm pretty excited by. This is something that we've been working on more recently as a result of working with a bunch of these different proof systems, and like, how do we not use sort of the syntax of the proof systems directly so that we can actually have a nicer experience using these proof systems, and hopefully we'll make this tooling, available to other people as well. We're working on a sort of like simple embedded DSL within BlockE2 that evaluates the expressions in your language as in CPU values, and also compiles those same expressions to in-circuit targets. So you can see like right there, this is like a super simple expression language. Let's say you have like a constant like big uint. You might have a bool. You might want to add two things together. You might want to multiply two things together. But kind of the advantages of this is like it sort of like abstracts the semantics of the builder interface that you have within BlockE2 away from like the person that's actually implementing this stuff. It also improves the auditability and readability of these in-circuit programs. So every time you do something like builder.add and you try to put your operations there, you don't need to do that. You don't really need to do that anymore. You're just sort of you look at the paper that you're trying to implement, take that stuff and copy it over into BlockE2. It makes it a lot easier and nicer to use. It also improves like the test and validation efficiency and life cycle of your program. So instead of having to just sort of sit there and say, okay, I'm gonna write this test and validate it against this other library, like I can write like 50 tests, in a few minutes, as opposed to just a single test that takes an hour because you're just, playing with bit strings all day. So the other thing that I think is super exciting about this is that we can sort of encode proof recursion directly into this DSL and abstract that away from the implementer as well. So instead of having to write these generators that are allowing you to do your proof recursion, you can sort of just encode that in the compilation step. So you just say, okay, I would like to add recursion at these lines, at these levels, and at this level of granularity, and it should just do it for you. And I think that's going to be very exciting, especially as people start using these different libraries, want to do proof recursion super efficiently, but don't really want to think about like what are the real intricacies of using these different like tools. Okay, cool. So another thing that's super exciting about this framework, or I guess framework of embedded DSLs, is like kind of new optimization paradigms, right? So this is kind of like a more PL term, but hash consing basically is this idea of like, abstracting over the semantics of your program and the structure of your expressions. So let's say you have an expression in your program that you've already seen before, right? Instead of just like evaluating the expression again, you should just be able to look up the value, right? And so this kind of like allows you to do that. And this is sort of like a standard sort of trick that's used in PL as well, and that's something that we want to bring to the BlockE2 ecosystem and so to some of these different proof systems. The other thing that we can do is actually directly encode optimizations at the evaluation step. So instead of just adding, let's say, two in-circuit representations together, using whatever operator exists within that proof system, we can just evaluate the addition or whatever operation in CPU and then construct the in-circuit representation from that. Another example of this is like, let's say you're doing scalar multiplication or exponentiation. You can just directly encode the most an optimal algorithm for doing that, right? So the naive implementation is like exponential. If you use double and add, it's linear effectively, right? So it kind of reduces the complexity by an exponential time, but you can just directly sort of encode this in the evaluation step. So every time you use that function, it's already being optimized. So another example of this is like simplifying in-circuit conditional. So a lot of you have probably come across this canonical example in circuits where like you have to represent both cases of your conditional, and that's sort of, and then you sort of have to like add these two cases together, and that's not really how you think about programs when you're programming in the non sort of like circuit world. And I think this is going to be like something that people will hopefully find a lot easier to write. All right, so what are we trying to do with all of these things? So let me just summarize. So we worked on a bunch of stuff related to like sort of like Merkle inclusion proofs, ETH serialization, and then kind of doing signature verification of BLS. I said why we started with ETH, but obviously we want to move to other chains as well. And so working on some of the ZK light client infrastructure for non-EVM chains, Ethereum, non-Ethereum chains. We want to work on some of the cryptographic primitives that enable this. So like, let's say EDDSA signature verification or ED25519 signature verification for, let's say, like Cosmos or Integrament consensus. And then we want to work on faster and more optimized proof generation for this stuff. So there's a ton of work that was going on the Z Prize last year, especially on FPGA acceleration and GPU acceleration. We want to take some of this stuff and kind of at least enable some of these primitives to work on hardware as well. And then, again, improve developer ergonomics and additional sort of like DSL features so that people, when they're using these proof systems, don't have such a horrible time trying to bootstrap into the ecosystem. All right, that's it. Thanks.
I actually have a question. The DSL, does it have a name? Is that Biscotti?
So it doesn't have a name, but if you have a name of an Italian cookie you'd like to use or dessert, we'll highly consider that. Yeah.
Okay, it doesn't have a name yet then?
No, it doesn't, yeah.
Okay. Which like Biscotti, though, is that the larger construction? Is that the name of it?
It's the larger thing.
Okay,
yeah.
Got it. Are there any other questions about this? Oh, we have a few questions. That's perfect. I think we have time.
Oh, yeah. I was wondering if you could comment a bit on kind of like the performance, especially compared to some other sync community implementations, like succinct, like how many gates, like on-chain verification, things like that.
Yeah, so we're not releasing any numbers right now, but we will soon. I just don't want to like talk about the performance yet until we have the full thing, sort of like where you can like review the code and look at it. So.
Hey, thank you very much for the talk. I'm just curious, what was the motivation for starting this project?
Yeah, there's a few motivations. I think, generally speaking, light client infrastructure is sort of like lacking within the ecosystem. I think a really efficient way to do this, obviously, is using ZK. For a long time, it didn't really seem like that practical to do this, especially because you need super efficient proof generation. There's a lot of other applications, for example, bridges, cross-chain messaging protocols, ZK oracles. Like a lot of this stuff requires some of this infrastructure, and like so, a jump, we try to contribute to a lot of infrastructure. So this is the motivation for that.
There's one more here.
Hey, thanks for the nice talk. So you're building ZK Light Prime proofs for the Altair Sync Committee, not an alternative to it, right?
Yeah, this is for the Sync Committee in particular, yeah.
And specifically for bridges?
Sorry, could you say that again?
Specifically for bridges.
No, this is sort of just generally like,
okay.
This is general like light client infra, yeah.
But so for bridges, the problem that you've got is, so the sync committee can post, can sign the correct block on-chain and can sign a fraudulent block for the light clients, and it doesn't have any way to prevent that.
Yeah, so the sync committee, there's no way to prevent that. This initial implementation uses the sync committee. We plan to expand it to the full validator set.
Okay, great.
Yep.
There was another question over here. And if there are any other questions,
Hi,
maybe just put
thank you
them in.
for the talk. Have you thought about the business models and whether you are looking at this as a infrastructure, public infrastructure, or more of a proprietary software?
Yeah, we have no plan so far in terms of like, there's no business model attached to this. This is just sort of like stuff we've built, so, you know.
There's one over there. If there are any other questions, just put your hands up now so I can. You have one? You have one? Okay.
Yes, I wanted to clarify. Right now, it's not available to to play with it. Is it It's not released right now, as I understand. But is it available to dig into it deeper somewhere or not?
Yeah, so we'll release the code soon. It'll be up on GitHub, and you can look at it. So
Okay.
we just haven't like released it yet. Yeah.
There I can follow now to find out updates. Just on Jump, yeah.
Gary, so did you say that again?
There I can follow updates on this topic. I don't know. Do you have some specific?
Oh yeah, check out our Twitter.
Just Twitter. Okay.
Okay, there's one here, and then one there, or then one there, and then one there. And then I think we wrap up, because I think, yeah, we're kind of at time.
Who's the first?
I have a quick question. Why make the DSL in Rust, or like this like quasi layer on top of Rust, instead of a language that has like nicer metaprogramming abilities?
Yeah, one reason is that because, well, we're already working with BlockE2, we're already working with Rust, and this is more of like it started out as more of like an internal tool. Like we just were very frustrated with using the syntax that exists already, and so we said, why not just do this? I think the other thing is that there are already a lot of, sort of like ZK DSLs that exist and are out there in the ecosystem, and we're not necessarily trying to compete with them. We're just trying to provide better dev ergonomics in a particular way, right? And for a particular proof system in a particular language. So
There's a question over here.
Hey, are you familiar with the Unison programming language?
I am not.
Okay, I wondered if you had taken inspiration from it, because it reminded me of what you were talking about. Unison, it's a functional programming language where the names of functions are determined by a hash of the kind of combinator primitives that go into it. And there's all kinds of benefits that you get out of that. You're probably discovering some of them with what you're doing, so it might be worth looking into. They've been working on this for a lot of years. They've come up with a lot of kind of cool things you can do once you're in that kind of world.
Cool, I'll take a look.
Okay, we have one back there. And then I think we'll wrap up on that. I think if that's okay. I guess after, if they have more questions, they can chat with you directly,
Yeah.
right? Perfect.
Have you done sort of benchmarking on how long it would take you to prove 400,000 signatures right now?
We haven't done a benchmark on 100,000 signatures, but
Do you think it's plausible in under 12 minutes?
potentially. I mean, I have a decent idea of like what kind of hardware you would need to do that. I don't think you need to, when you say prove, on the order of 100,000 signatures, like that's not really what you're doing, because you have like in the Ethereum protocol, you have like a set of like aggregate signatures that you need to prove, and so it's mostly just doing a bunch of aggregation and then doing a bunch of let's say like a few hundred signature verifications. So that I think is probably feasible, but no comment on the other part.
All right. Thank you so much, Rahul. And thank you all for these questions.